For 70 years, we have built rockets by slowly burning fuel in a metal bell. A controlled fire, a raw push against gravity. But the future of space travel is not about burning fuel at all. It is about detonating it. Right now, engineers are building engines that ride supersonic explosions, not just to go faster, but to change how we leave this planet. This is the story of how we stopped burning fuel and started detonating it. Space does not forgive mistakes. Every kilogram we lift off Earth costs a fortune, and every ounce of efficiency squeezed out of a rocket engine counts. For decades, rocket propulsion has relied on deflagration. Picture a controlled campfire. Fuel and oxidizer mix, ignite, and burn at subsonic speeds, pushing hot gas out the back. It works, but it hits a ceiling, limited by the speed at which that flame front can travel. We have pushed deflagration engines absurdly far. Engines generating millions of pounds of thrust have sent humans to the moon and probes to the outer edges of our solar system. But engineers always want more power, more efficiency, packed into a smaller, lighter frame. And that hunger is exactly what led to detonation. Detonation is a different animal. Instead of a slow burn, you get a supersonic shockwave, a controlled explosion traveling faster than the speed of sound, compressing fuel and oxidizers so violently that they ignite almost instantaneously. This is not just a faster burn, it is a different chemical process entirely. In a traditional engine, pressure actually drops during combustion. In a detonation, pressure rises. Engineers call this pressure gain, and it is the holy grail of rocket propulsion. More pressure means more thrust from less fuel in a smaller engine. The concept has tempted engineers for decades, but it was always written off as too unstable, too wild to control. And then came 3D printing. For a long time, the rotating detonation rocket engine, or RDRE, lived only on paper. Containing a continuous supersonic explosion without the engine ripping itself apart demanded geometry so complex and materials so advanced that traditional manufacturing could not touch it. 3D printing changed that, not as a convenience, but as the thing that made the physics possible in the first place. We are not talking about a desktop plastic printer here. We are talking about massive robotic systems that print entire rocket components from exotic metal alloys. Relativity Space built their Stargate printers, some of the largest metal 3D printers on Earth, and they can print a full rocket like their Terran R in just 60 days. The part count drops from over 100,000 individual pieces to under 1,000. Every weld, every bolt, every joint is a potential failure point, and printing a component as a single monolithic piece wipes those weaknesses off the table. The company calls it software-defined manufacturing. If a part needs a tweak, nobody retools a factory. They update the CAD file and print a new one. Tim Ellis, the CEO of Relativity Space, puts it plainly. 3D printing is automation for aerospace. Materials matter just as much as geometry. You cannot print a rocket engine out of any ordinary metal when it operates at extreme temperatures and pressures. NASA developed GR-COP42 for exactly this problem, an alloy of copper, chromium, and niobium built specifically for additive manufacturing. GR-COP42 withstands temperatures up to 6,000 degrees Fahrenheit while keeping exceptional thermal conductivity. That property lets engineers print intricate internal cooling channels, mimicking the vascular system of a living organism, keeping the engine from melting under the sustained heat of a detonation wave. The printing technique itself is called directed energy deposition, where a laser melts blown metal powder as a robotic arm builds the structure layer by microscopic layer. Now back to the explosion itself. Inside an RDRE, multiple detonation waves, usually 3 to 6, chase each other around an annular combustion chamber thousands of times per second. A continuous controlled explosion, a ring of fire generating immense power. NASA Marshall Space Flight Center has led much of this testing, successfully hot-firing components at 4,000 pounds of thrust and even running a full-scale engine at 10,000 pounds of thrust for record durations. More recently, Astrobotic tested their Chakram RDRE and hit 4,000 pounds of thrust as well, proving this technology is jumping from the lab to commercial hardware. But there are still rough edges. The sound of an RDRE is not a roar, it is a scream. High-frequency detonation waves produce an acoustic profile unlike anything heard from a rocket before. And while 3D printing allows for wild complexity, the surface finish can still be rough, adding a slight mass penalty. Engineers are still refining the process, making sure these engines are not just powerful, but reliable enough to carry people. We usually talk about the future of space in terms of destinations, the moon, Mars, maybe beyond. But that future is being built right here on Earth. in foundries and labs where engineers are reinventing the very machines that carry us off the ground. The 3D printed explosion is more than a new engine type. It is a complete rethinking of how rockets get made. By adopting radical manufacturing techniques, engineers can now work with physics that were once dismissed as too dangerous, too complex, or just flat out impossible. We are building rockets with the precision of a surgeon and the speed of a software update. And this is not only about reaching Mars faster or cheaper. It is about building an industrial base on Mars, printing habitats, tools, and even new rockets from local materials, making humanity genuinely multiplanetary. A strange thought. The future of our species might hinge on a machine that prints its own explosions. But space has a way of turning the most audacious ideas into the most logical next step. Really quite the feat of engineering, the 3D printed explosion. Oh, and if these engines become 100% reusable, launching a rocket might cost about the same as a plane ticket. But that is a story for another time.